Hello, welcome to lecture 2. Today I am going to talk about relations and functions. This is mathematics for class 11 based on chapter 2 and also based on NCERT syllabus. My name is Sangam Banerjee and my details are given below. So what is relations and functions? Here relations involving pair of objects. So we will only consider pair of objects like brothers and sisters. This is a relation. Father and son, then teacher and student. Number m is less than number n. These are all relations. Line L is parallel to line m. So how line L is related to line m, or set A is a subset of set B. Okay, so how set A is related to set B. So these are all relation, and in this lecture we will learn how to link pair of objects from two sets and then introduce relation between the two objects in the pair. And also there will be some special relation which will qualify to be a functions. So mathematically functions captures the idea of a relationship between one quantity with respect to another quantity. So we will see this in next few slides. So if you have an input say x and you operate by function f, you get an output, we call it y. So here a function is a relation where each input has only one output. So if each input has say two output, then it is not a function. So it should have only one output. So this way is also allowed. Say this is an input, it has one output. Also second input, this is also one output here. These are allowed. So 1 to 1 is allowed or many to 1 is allowed, but 1 to many or many to many is not allowed. You should not have here many. So this is how you remember. Suppose one input and there are many output, it is not a function. We have studied extensively in class 9th and 10th how to plot a graph or a function. This is a linear function. This is a constant. This is also a constant. Here in this y is constant and here x is constant. This is a parabola which is shifted. We have studied this extensively. I would recommend you all to please go to my class 9th and 10th lectures. It will not take much time and it will be a good revision. So there is a vertical line test for function. So if you draw a vertical line and it cuts this relation only once, then you call it a function. So here this is a function, here this is also a function, here also if you draw any vertical line it will cut only once, this red curve here, which is this is a parabola shifted down, but this parabola is not a function. If you draw a vertical line here it cuts in two places, so this we will not consider as function. Again this is a function, again this is not a function, it is cutting this relation twice, and also if you draw a vertical line on a circle here, so this is cutting twice, so this is also not a function. So similarly here I can break the function in two domain, that is x less than equal to 2. So this is equal to 2, I put a solid dot and this is your relation, and for x greater than 2, so this is not equal to, so this is open circle where we have discussed in earlier lecture what do you mean by open interval and closed interval. This is a closed interval at 2 and this is line is an open interval because 2 doesn't belong to this function. Now let us check the vertical line test for this function. So here if I draw a vertical line here at say x equal to 2, it will cut the function at this point, but if I move the vertical line slightly greater than 2, that is x greater than 2, so here you see it will cut this function because this point is not equal to 2 but very close to 2, okay, which is greater than 2, and hence this is a function. This is unlike here you see for x, one value of x you have so many values of y goes from minus infinity to plus infinity, so this is not a function. Unlike here you see if I draw a vertical line it will only intersect at one point for any given x. Similarly like here as I had explained earlier, if I draw a vertical line it will cut this red curve at only one place. So now we discuss what is order pairs x comma y. An ordered pair is a pair of number in a specific order, so it has to be in a specific order. If you change the order then the meaning may change, so this you have to remember. And here I give you some set of ordered pairs. So here you can see for each input there is a unique output, so this is 1 and 5, but here you see there are two inputs are there, but again this 5 is repeating, but this is allowed because each input should have only one. So if it had been here 1 comma 5 and say 1 comma 6, this is not a function because you have two same input but two different out, but this is a function. So similarly here you see what I have said earlier, this is 10 comma minus 20 and then 10 comma 5, so this is not a function. So note here you have to maintain the order here, you cannot just flip this. So from here you can see that functions have no repeating x's with different y values, and so we can conclude that all functions are relations but all relations are not functions. So these are all relations but they are not functions, only these are the functions based on these conditions. Okay, now we will introduce Cartesian product. So what is Cartesian product? The Cartesian product of two non-empty sets A and set B denoted by A cross B. This is how you denote the Cartesian product. Is a set of all ordered paired A comma B where A is an element of A and B belongs to B. B is an element of B means B belongs to B. So I can write the set A cross B in a set builder form, that is A cross B is equal to this this ordered pair A comma B, this is small a and B, small b, such that A belongs to A and B belongs to B, where this caret is actually is a symbol for AND. So to explain it to you much better, suppose this is set A contains element X, Y and Z, and set B contains element 1, 2 and 3. Then the cross product will be X comma 1, then X comma 2, X comma 3. So you will have like this 9 combinations. So these are the elements, and I can write A cross B equal to all these elements in this. So here is an example. Suppose I tabulate these meals and drink, and each one of them get one meal and one drink. So how many combinations are there? So meal name and drink name. You have omelette, fried egg, sausage. So these are the 3 meals, and it can go with orange juice. Again, this same 3 meals can go with tea, and again this same meal can go with coffee. So you have altogether how many? 9 combinations. So this is how you can represent in a matrix form also. So here I can write X as omelette, Y as fried egg, sausage as Z, and drink here. Okay, so this is in a matrix form. So this Cartesian word is in honor of a French philosopher René Descartes from his Latinized name Cartesian. So an ordered pair A comma B consists of 2 values A and B. Their order of appearance is important, as I mentioned earlier. So we call them first element. This is as the first element and second element respectively. So as I said, note consequently A comma B is not equal to B comma A unless A equal to B. In general, A comma B equal to C comma D if and only if. So this is another short notation of if and only if A equal to C and B equal to D. So if these two are equal, A equal to C and B equal to D, then these two order pair are same. And as we have seen here, the number of element in Cartesian product of 2 sets, this is 2 sets, set A and B. Suppose if number of element in set A is P and number of element in set B is Q, then the number of element in the Cartesian product of A cross B is equal to P times Q. Now we will discuss what is domain, codomain and range. Now suppose you have 2 sets, set A and set B, and these are the relations marked by arrow, and here relations are these arrows, that is -1 to 2, then 0 to 3. So all these arrows are written here as an ordered pair. And what is the domain? You are using all of them. So -1, 0, 1, 2. So all of them is a domain because you have used all of them. And what is codomain? This whole set is a codomain, including this 4 which you have not used also. So here I have written 4. And what is range? Range is simply the output. And this was not output of any of this input. So range will be 1, 2, 3 and 5. You don't have to write this 4. If you write 4, then it becomes a codomain. So in other words, if you have a set A, this is domain, and then some of the elements has been used and you get range, and the element of range and the remaining one total is called the codomain. It will become more clear now. Suppose this is a domain and each has this relation, but these are left out. So this region is the range, and this relation is f of x is equal to x square. So 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, and 5 square is 25. So this is range, and the total, this in green, is the codomain. Now another example, here let x have a relation that it goes to 2x plus 1. So this 1 becomes 2x plus 1 is 3, then 2x, that is 2 into 2, 4 plus 1 is 5. Similarly for 3 and 4. So these are the range, 3, 5, 7, 9 are the range, and this total set B is the codomain, and this is the domain because all are been used. So sometimes this range is also called as image. So here let us review it. Given a function f such that A goes to B, we say f maps A to B. Okay, this is the function, it maps from A to B, or f is mapping from A to B. A is called the domain, this is called the domain, B is called the codomain, and if f of A equal to B, so suppose f of 1 equal to 3, so then B is called the image. So this is the image of 1, that is image of A under f, and A is called the pre-image of B, and this is called the pre-image. Okay, if suppose this is A, this is B, then this is your image and this is your pre-image. And the range of f is set of all images of points in A under f. We denote it by f of this set A. So now one can write domain in a set builder form, that is domain of a relation R equal to A such that ordered pair A comma B belong to real number. Here R is a real number. Here I should have used a different notation, but I am following your textbook, so there they have used this notation, but it is okay as long as you know what it means. Now range in a set builder form, that is range of a relation R is equal to B. This is B of the ordered pair A comma B belongs to R. Here again R is a real number. So to note, the variable denotes the set of real number, that is every value in the domain belongs to the set of real numbers. So similarly, I can say that codomain of relation R from set A to B. So codomain will be full set B, as I had shown in earlier slide using a diagram. Okay. So obviously range is a subset of codomain, which I have mentioned that too in in earlier slide. Now another statement, if set A and set B are non-empty sets and either set A or set B is an infinite set, then so is A cross B. Okay, the Cartesian product will also become a infinite. Now you can have Cartesian product of higher order, that is 3 set A cross A, that is equal to, I can write an order triplet here. So it has to be ordered. This A, B and C belong to A, but if suppose there are different sets, then each individual will belong to that respective set. And this we will not discuss much in this lecture as this is beyond the scope of class 11 syllabus. So as we have shown earlier that A cross B can be represented in a two-dimensional matrix form, and this three-set Cartesian cross product can be represented by three-dimensional array. Anyway, we are not going to discuss any further regarding this. Now let us do one example from your textbook, that is, let set A equal to 1, 2, 3, this is B and this is set C. Find this Cartesian product of A cross B intersection C and then intersection of these two Cartesian product and Cartesian product of A cross B union C, and similarly union of these two Cartesian products. So these are very simple. So first you evaluate B intersection C, so common is 4, so B intersection is 4. Then you take a cross product with this A, so you will have 1, 4, then 2, 4 and 3, 4. So this is the Cartesian product of A and B intersection C. So similarly, to find this, you first find the Cartesian cross product of this and find the Cartesian cross product of this, and then from these two you find the common element. This is intersection, and here it is shown. Just pause it and go through it. This is A cross B, you have this. A cross C, you have so many elements, and the common are only 1, 4, 2, 4 and 3, 4. So this is your answer. So similarly for third, you first find the B union C and then take a Cartesian cross product of B union C, which you can see here. And similarly for this, as we have done earlier for these two, you find the cross product of this and cross product of this and take a union. So you will get all this set of ordered pair. Now an example, if set P is this element 1, 2, form the set P cross P cross P. So here for each P you write this in braces 1, 2 cross again 1, 2 and again cross 1, 2. So now from each of these you take 1, 1, 1. So this is 1. Then you take 1, 1 and from this only take 2. So this is the 1. So you take all this combination and you will get this set. So this is like a 3D array which I had mentioned earlier. Now let us discuss examples of functions and not functions. So this y is equal to 2x square minus 8. Definitely for each x you have only one output. So it is a function. And similarly for this x square plus y square is 25 is not a function, because I can get, if I take this x square here, 25 minus x square, and then y square, if I take a square root of it, so it can be either plus or minus. So now for a given x you have 2y. Okay, so this is not a function. But if I say it is plus instead of plus minus, then it is a function. So why this is a function I have explained here. You see here x, it goes more than 5, then this becomes a negative number, so it will be a complex number. So it has a range from minus 5 to 5, and beyond that value this quantity will become negative and it will become a complex number. So here the interval notation I write from minus 5, here I have drawn here minus 5 to plus 5, and x belongs to minus 5, 5. So in a set builder notation, it is x such that minus 5 is less than equal to x is less than equal to 5. So the domain is all the values of x that makes the expression defined, okay, this expression, and range are the values of f of x where y belong to from here 0 to 5. So these are the values of range from 0 to 5, and from minus 5 to plus 5 are the values of domain. Now for this equation, if I bring x here, this becomes plus 2x, and then y cube becomes cube root. Now here you see for any x you don't have an ambiguity, so it has a unique value, so hence it is a function. So now if you have a set here called P, which is nothing but a square of the element in Q, I can write at this x is equal to y square, then definitely this is 1 too many. That means that 9 is either plus 3 square or minus 3 square. And similarly here, so this is not a function, but obviously this has a relation, and we write the relation is x is a square of y. And in a set builder form, I can write this relation R is nothing but x comma y, such that x is the square of y and x belongs to P and y belong to Q, which we have shown here. And in roster form, I can write as 9, 3, 9, minus 3, and so on, so 4, 2, 4, minus 2, and similarly 25, 5 and 25, minus. Okay, so these are the ordered pair, and this is the relation R. And the domain of this relation is your 4, 9 and 25, which I have written here. And the range of this relation is, you have to consider only this output which are been marked by arrow, that is minus 2, plus 2, minus 3, plus 3, minus 5, plus 5. So note here in set these orders are not so important like in ordered pair. So note that the element 1 is not related to any element in P, and the set Q is the codomain of this relation. So the relation from set P to Q is not a function as we mentioned earlier, because single input has more than one output, one too many. Now note here, if set A contains 2 elements and set B contains 3 elements, that is 3, 4 and 5, then the Cartesian product of set A and B consists of 6 ordered pair. These are the one, that is 1, 3, then 1, 4, 1, 5 and 2, 3, 2, 4 and 2, 5. And since the cardinality of set A is 2, there are 2 elements, and the cardinality of set B is 3, there are 3 elements. So we have number of elements in the Cartesian product of set A and B equal to 6. This 2 times this 3 is 6. So number of element in set A is 2 and number of element in set B is 3. So product of this will give you the total number of element or the ordered pair in the set of Cartesian product of set A and B. In our previous lecture we have shown in lecture 1 by induction method that if the number of element in A is, this is n of A is m, then the number of element in the power set of A is 2 to the power m. So please kindly go to my previous lecture and see this proof. And note here, this is slightly different from what I have said it here and what we have said it in the previous slide. So go to the previous slide and check it. So now one can say that the number of relation, if number of element in set A is P and number of element in set B is Q, then the number of relation from set A to set B, that is the number of subset of A cross B, is given by 2 to the power P times Q. This is slightly different from what we have said here. Just in the previous slide you see those definition. Here all combination, this is a power set of A. So you please see the definition of power set of A which we have discussed in lecture 1. Now we will discuss real function and real valued function. So now if you consider two sets, set A and set B, where all the elements in set A belongs to real number, or one can say that set A is a subset of real number, then there is a function f such that A is mapped to B and all these elements in this set B are real number, or you can say this set B is a subset of real number, then this is called the range and all these elements in A are called the domain. So let us now see an example. This is f of x is equal to x square. So this is like a parabola x square. So here you have a domain from x equal to minus infinity to plus infinity. This is a domain, and this x square will be something like, it's a parabola as I said, say from 0 it starts and it goes, this is a parabola function, and in the negative x axis also it is will go like this. So all the values in the y axis from 0 to infinity. So here what I have written here, this is the domain and this is the range from 0 to infinity. As I said that the parabola goes like this and here also goes like this, and you have only this y value which goes from 0 to infinity. Or one can write as domain D equal to minus infinity to plus infinity, and the range of x which maps to x square is 0 comma plus infinity, and here you see is a square bracket, that means 0 is also included. So at x is equal to 0, f of x which is y is also equal to 0. So that's why we put a 0. So this point is included in the range. To plus infinity is open, so you do not know where it ends. Now example 2, this is f of x is equal to square root of x square minus 9. So here you see this x square should be greater than 9. If x square is less than 9, then this becomes a negative number, and square root of a negative number is an imaginary number. This imaginary number belongs to a complex number, and maybe in other lecture I will discuss about this imaginary number, or which is same as a complex number. So here f of x is equal to square root of x square minus 9. This function will go, say this is your x axis. Of course, as I said, for x less than 3 it will be an imaginary, so we don't consider. So for x greater than or equal to, here I should have put a closed circle, but here by mistake I have put open circle. So consider this as a closed circle. So your function will go something like this, and also in the negative x-axis your function will go something like this. So your y value will be from 0 to infinity, because this function is going like this and here also is going like this, and so you have only this y value in the positive y-axis but not in the negative axis. So you have this domain from minus 3 to minus infinity, and this side it is from plus 3 to plus infinity. So I can write this as domain is minus infinity to minus 3. This is a square. This should be a closed circle. So union of this plus this is 3 to plus infinity, and the range of x going to the square root of x square minus 9 is 0. Again this 0 is included because for x equal to 3 square is 9 minus 9 is 0, so this should be 0. So 0 is included to plus infinity. So this is a range. So you also have a real valued function. In a real valued function function is very similar to this, except that this set A, the element may not belong to real number. And here set B, the range, the element of set B belongs to real number, or set B is a subset of a real number. So I define it here, a real function, a function f such that A goes to B is said to be real function if A is a subset of R, if this is a subset of R and also this B is a subset of. Whereas in a real valued function, only range is a subset of. Okay, this is what I have written here. F such that A goes to B is said to be real valued function if and only if B is a subset of R. Now some functions and their graph. So we have an identity function. So identity function means if you have, say, if you plot xy, this is xy plot and x is equal to y. So here I have written let the real value function f such that R goes to R by y equal to fx is equal to x. So here y is equal to x for each x belong to R. So this is your identity function. Similarly, you have a constant function. This is your constant function. That is y equal to c is all constant for all x. So here the domain of x is R. Okay, it can be anywhere shifted and its range is c. So its range is only one value, that is c. And then the polynomial function, this is your polynomial function. Y is equal to fx is equal to this a naught. These are the coefficient a1, a2 up to an. These are the coefficient. And this is x to the power 1, x to the power 2 and so on till x to the power n. So a function f such that R goes to R is said to be polynomial function if for each x belong to R you obeys this one, where n is a non-negative integer. Okay, these are non-negative integers, these are all positive integer, and a0, a1, a2 up to an, they belong to, these coefficients belong to R. The function defined by f of x is equal to x cube minus x square plus 2 and gx is equal to x to the power 4, this is the coefficient x, are some examples of the polynomial function. But h of x is equal to x to the power 2 by 3, this is not a natural number, not an integer, so we cannot designate this as a polynomial function. And then you have a rational function. These are functions of the type f of x by g of x, where f of x and g of x are the polynomial. Function of x defined in a domain where g of x is not equal to 0. So this should not be equal to 0. Then it will blow up. So then it doesn't remain a function. And one of the example is here, you see f of x is equal to 1 by x. So at x is equal to 0, it blows up. It goes to infinity. So you have to write here the function is valid for all x except x not equal to 0. So you have other type of functions also, the modulus function. So this is a modulus function. So this is x. For negative x, you put a mod of x. That is, here I have shown f of x is equal to mod of x. So if minus x will become plus and plus x of course will remain plus x. So this is the modulus function, and the modulus function, the function f such that R maps to R defined by f of x is equal to mod of x for each x belong to R is called the modulus function. What I have said here. And then you have a signum function. So it's like a step function here. So here you see at 0 this y value 1 is not included, and here y value of minus 1 is also not included. So I can write f of x equal to 1. So this is y equal to 1, or it equal to 0, it is 0. For 0, x is equal to 0, it is 0, y is equal to 0. And for x less than 0, it is not equal to here. So it is all less than 0. So this is why it is kept an open here. So this is minus 1. So this is called the signum function, a function defined by this function. So this is also sometimes called as a step function. We will see in higher classes. Now we see what is greatest integer function. So here I have given the definition. The greatest integer function of function f is such that R goes to R defined by f of x equal to, this is in square bracket. This square bracket means it has some condition. Here the conditions are given. This is this x equal to minus 1 for minus 1 less than equal to x less than 0. This is minus 1. Then here it is 0 for 0 to less than 1. Then it is 1 for 0 to less than 2. You see this 2 is not included. It is not equal to sign here. So you keep an open circle here. Similarly here x equal to 2. This x equal to 2 for 2 less than equal to. So here this point is here. So if you draw a vertical line test, so it will only cross 1. So if it is 2, it will touch here. But this point is not there actually. It is less than 2 here. So even if you do a vertical line test, it will pass this test. Okay. So it is a function. So this is how you represent a function. So here as I had said that here x belong to R assumes the value of the greatest integer less than or equal to x. And such a function is called the greatest integer function. Now algebra of a real function. So here I have just cut and paste here to save my time. So here we see what is addition of two real function. Okay. So if you have function f and g, so f plus g, just go through this. These are self-explanatory. So if you have f plus g of x, it will be f of x plus g of x for all x belong to x. Similarly for subtraction also, f minus g of x is equal to f of x minus gx for all x belong to x. Then you have multiplication by a scalar. Scalar means some constant number. So if you, this is your scalar number alpha, if you multiply to f, so you get alpha times f of x as alpha times f of x, where x belong to x. Okay, these are all very trivial. And multiplication of two real function, that is if you have f and g, so this is the function f times g, f into g, I can write as f into g of x is f of x times g of x for all x belong to this set x. This is also called a pointwise multiplication. And quotient means the division of two real functions. Suppose you have f and g as a two real function, then you can define f divided by g as f divided by g of x is nothing but f of x divided by g of x, provided that this g of x is not equal to 0 and x belong to the set x. So now let us see some example. These are also taken from your textbooks. Let f of x is equal to x square and g of x is equal to 2x plus 1 be the two real function. Find f plus g of x and f minus g of x and f into g of x and f divided by g of x. Okay, so it is very simple, just simply add it. This is f plus g of x is nothing but f of x plus g of x. So f of x is your x square plus g of x. So similarly f minus g, just it is self-explanatory, just go through it. I am just showing here so that you get confident that these are so trivial. Okay, so here f into g of x is f of x into g of x. F of x is x square and g of x is 2x. So you multiply this, you get this answer. Similarly, f divided by g of x is f of x is x square here, okay, and g of x is 2x plus 1. So you do, and here you have to know that this denominator should not become 0. So when it will not become 0, or when will it become 0? At x equal to minus 1 by 2. Okay, so you should not have x equal to minus half. So it should not be. This is the condition. There is another trivial example. Find the range of each of the following functions. So suppose you have given function f of x is 2 minus 3x, where x belong to R and x is greater than 0. What is the range? So here range will be your x can go to a very large number. So this will become negative. So when x is equal to 0, you have 2. And as x increases from 2, it will start reducing and it will go up to minus infinity. Because at x very large number, this becomes very large negative number. Similarly here for f of x is equal to x square plus 2. You know, for x is equal to 0, you have 2. So you can start with 2, and then as you increase the number, and whether it is negative x or positive x, it will become positive only because it's square, and then it will go up to infinity. So it belongs to 2. 2 is a close here, and it goes up to infinity for this one. And for third, f of x is equal to x. X is a real number. So here range will be the whole real number, the negative number as well as positive number including 0. Now we will discuss some miscellaneous exercise on chapter 2, which I have again taken from your textbook. So I will briefly do the solution in the margin here. So these are all very simple exercises. I am just doing it to show you that how simple these exercises are. So here let f equal to, this is the set, be a function from z to z defined by f of x is equal to ax plus b. So this is your first element. This is for the domain a, and this is b is the range for some integer a and b. Determine a and b. Okay, so this is also not very difficult. So this is the value of f of x is given here 1 3 minus 1. This is the value of y. So using this one for x equal to 1, I can write here this 1 equal to a plus b. Okay, this is because x is 1, and I use this one. So 3 equal to here ax plus b, and here x is equal to 2 here. So I write 3 is equal to 2a plus b. So now I have two equations and two unknown. So it is possible to get it. So I multiply this by 2. So I can cancel this 2, and then your 2b minus b is b. So b equal to minus 1. And if I put b equal to minus 1, this minus 1 will go here, will become plus 1. So 1 plus 1 is 2. So a is 2. So these are so trivial. So these are not so difficult problems. So now the next problem, let R be the relation from n to n defined by R equal to this ordered pair a comma b such that a and b belongs to natural number and a equal to b square. So are the following true? So for this a comma a, this ordered pair belong to R for all a belong to n. So is it true? So here answer is no, because here if we use this condition, that is a equal to b square, for this one I have a equal to a square. And the solution for this is nothing but if I take a square in this side, or I bring a here, so I factorize it, a into a minus 1 equal to 0. So now I have two solution, either a equal to 1 or a equal to 0. So as I said, for single input you cannot have two solutions. So this is not valid. So similarly for a comma b implies b comma a belong to R. So here you see, if I apply this condition, you will get a equal to b square for this, and then for this it is b equal to a square. square, which is not possible. So hence this is not true for this. And the third one, that is if ordered pair A comma B belongs to R and ordered pair B comma C belongs to R, then ordered pair A comma C also belongs to R. Okay, so here as I said, if I use this condition here, A equal to B square, and here B is equal to C square, and now if I eliminate this B by substituting the B here, so I will get A equal to C square the whole square for this. So this is not true. This is not a similar condition what is mentioned here. So this is also not true. Now next exercise, let A equal to this 1 comma 2 comma 3 comma 4. These are the elements in set A, and elements in set B are given this, and the mapping of F is this 1 to 5, then 2 to 9, 3 to 1, then 4 to 5. This 4 goes to 5 here, and then 2 goes to 11. Okay, 2 comma 11. So these are the pair for this F. So are the following true? F is a relation from A to B. Yes, it is a relation because all the elements in this left hand side are belong to A, and all the elements in this parenthesis in the right hand side belongs to set B. So they form a relation. But if F is a function from A to B, so this is not a function from A to B because here you have two input here, this 1 and this 4 have a common output. Okay, so many to 1 it is not allowed. As I said, each input should have unique. So there are two input having same value, so it is not a function. So justify your answer in each case. So we have justified this. Now again, next exercise, again we will solve it in the margin. So let F be a subset of Z cross Z defined by F equal to this A B comma A plus B. So this is your A is the domain as I said earlier, and B is the range where A and belongs to Z, that is the integer. So is this function F a function from Z to Z? Justify your answer. So here I have said here for A equal to 0, suppose I take A equal to 0, okay, A into B is 0. So for different B you will have different A plus B. So for 0 then you will have different these values. So one too many, so F is not a function. So here F is not a function. And now here let A equal to this, these numbers are given here, and let F such that A goes to your natural number be defined by F of n is the highest prime factor of n. Find the range of F. So for this your highest prime factor is your 3, for this is 5, this is 11, for 12 again you have 3, and for 13 the prime factor highest is your 13. So I can write 3, then 5, then 11, then for this again 3, so you need not, since you have put once 3, you need not put it again, and then 13. So this is the range of F. Now I think this is the final example. I will, before ending, I will show this one. Let A, B, C be a non-empty set. Prove that the Cartesian product, that is A cross C, is a subset of B cross C if and only if A is a subset of B. So this we have to prove it. So how do you prove it? So you have two steps actually. Step 1 is that if we prove that if this is true, then you get this, or if this is true, then you get this. Then one can say that this statement is true. So in step 1, now I consider if this A cross C is a subset of B cross C, then I can say that this ordered pair A comma C is a subset of this A cross C. But your A cross C, I have considered this to be a subset of B cross C. That means it implies that A comma C belongs to B cross C, because I have said that this is a bigger set and this is a subset. So this, since this belongs to this smaller set, so this AC will definitely belong to this bigger set, that is B cross C. So if this belongs to B cross C, that means A belongs to B and C belongs to C. And now since A belongs to B, it means that A is a subset of B. So just pause and go through it. I am sure you will understand what I am saying. So now the other way around, step 2, if A is a subset of B, then let A comma C belongs to A cross C. But we have taken A as a subset of B, which implies that A belongs to B. And since A belongs to B, I can write that A comma C belongs to B cross C. And since A is a subset of B, I can write that A cross C is a subset of B cross C. So we could prove that because A is a subset of B, we have this. So thus we prove this statement. I think I will finish here, but before finishing completely, I would like to tell what we have covered. So here is a summary. Again, I have just cut paste from your book to save my time. So we have discussed in this chapter what is ordered paired, what is a Cartesian product. Then we have also said that if number of element in A is P and number of element in B is Q, then number of element in A cross B is P into Q. So this we have discussed. And this A cross phi is a null set. So anything cross product with phi is a null set, which is very obvious. And then in general, your Cartesian product of set A and B is not equal to Cartesian product of set B cross A. So why this is not equal? Because we are dealing with ordered pair. So if you change the order, then the meaning changes, as we saw it in meal and drink. Okay, if you change somewhere first meal and then drink, and in some cases first drink and then meal, then the meaning changes. We have discussed what relation is. A relation R from set A to set B is a subset of Cartesian product, which we have shown here, A cross B. So all the relations we have shown in matrix form obtained by describing the relationship between the first element X and the second element Y of the ordered pair in A cross. Then we have discussed image also. The image of an element X under relation R is given by Y, because this is in set B, this Y, and this X is in set A. So this is the image. So where X comma Y belong to real number, and the domain of R is set of all first element, as I said, in an ordered pair of the ordered pair in a relation R, and the range of the relation R is set of all second element of the ordered pair in relation R. And function, we have shown that a function f from set A to set B is specific type of relation for which every element of X of set A has one and only one image Y in set B, which we have discussed. We write f such that A maps to B where f of X equal to Y, and A is the domain and B is called the codomain of F. And then the range of a function is a set of all images, obviously, and a real function has a set of real numbers or one of the subset both as its domain and as its range. So both domain and range should have a real number. An algebra function we have just discussed. This is f plus g is f of x plus g of x, and f minus g of x is this. So which we have discussed. So I think with this we have covered this chapter on relations and functions. So thank you, and we will see you in next lecture.